Hey, everybody. We're just going to keep on moving forward. Those of you guys who don't know yet, there's been a bunch of stuff out from the board about final marks and midterm marks and things going to OUAC. So as of right now, everything after midterm will affect your mark only if it raises it. So once again, everything you do from this point on is risk-free for your mark. So let's say you're at a 95, you can only go higher if you obviously are getting over 95. So that's good news. The bad news is that really the marks don't matter. The marks don't matter, and really, once the marks don't matter, you need to start worrying about learning for next year, right? So as being grade 12s, you need to be able to do first year university physics. And the onus is on you to follow along. I'm going to keep on posting things, and it's going to be at a slower pace than usual because of the 3-hour limit of things that I can put out. But what I'm going to hopefully try and do is get you as much of the way through first year, at least that you know about things, and we'll try and work together on that. Okay, so marks don't matter, and your learning does. That's good, and really that's my philosophy anyways. So today we're going to go through conservation of momentum. We talked about this last week, where we did conservation of energy, where no energy is created or destroyed, only transformed from one form to the other. So EK to EP, or EK plus EP into heat for total mechanical energy. So conservation of momentum, and you guys, I think, were able to calculate momentum. So once you've calculated momentum, momentum is just mass times velocity of an object. And so conservation of momentum is just that momentum is not created or destroyed, only transformed from one form to the other when two things collide. So just a quick summary of last week. So conservation of energy and momentum. So the law of conservation, a generic version is blank. So whether it be energy, momentum, mass, cannot be created or destroyed, only transformed from one form to the other. Conservation of energy says that the total mechanical energy at one point is equal to the total mechanical energy at the other point. So the total mechanical energy, once again, is the sum of EK plus EP plus Q. Q being heat energy, so Q equals MC delta T. So the total mechanical energy at one point is going to be the same at the other point. So this is where if we were in a classroom, we'd bring out that pendulum again. I'd put it up against my face. It would go out, and then I'd be scared and I'd flinch. But technically, the law of physics says that energy won't change at all. So it's going to stay right in front of my nose. So this calculation of a 2-kilogram bowling ball going down on a pendulum, sweeping across from a 5-meter height, I would get you, if we were in class, to calculate how fast the ball is moving at the point right above someone's desk. I think Michaela sits on that side. So right before it goes in between Michaela and Maggie. So all we would do is we would say that the total mechanical energy at the top is equal to the total mechanical energy at the bottom 1 meter above. So mgh plus 1/2 mv squared equals mgh plus 1/2 mv squared. And so we're going to just rearrange. And so for this particular situation, we're going to say that the velocity is 8.85 meters per second right above the top. So let's get into conservation of linear momentum. Linear means in a straight line. Next week, we're going to do conservation of momentum in 2 different directions. And we'll work with that. So what is momentum? Momentum is a quantity of motion. It's linked to the inertia. And so remember, inertia of an object is just a direct correlation with how much mass an object has. So inertia is the ability of an object to be moved by a force, right? So not moved, its motion changed at any point. Okay, so a big boulder is going to have a much bigger mass, and therefore you're going to need to push much harder to change its motion, whether it's coming at you or you're just trying to push it from rest. In order to change its motion, you're going to need a lot more energy to change its particular path. What we're going to do is that this whole unit is we're going to start looking at the collisions between objects. So when two things crash together, we're going to be able to predict both the magnitude of its velocity vector and the direction of its velocity vector. So whether it's coming in as a linear, so there's a bowling ball and a bowling pin coming together, you're going to be able to track where that pin is going to fly off. Or if it's two cars, T-bone crash, collision, we're gonna start predicting those collisions, which is kind of cool. Last week we talked about the impulse. One of my favorite labs that we get to do in this unit is using Bruce bucks for our auction for car bumpers. Obviously, we're not going to be able to do that, which is disappointing. So basically, all we want to do is that impulse is the force put on an object is equal to its change in momentum over time. And this is where we get to talk about how crumple zones in cars are able to take the energy from a crash, and as the crumple zone increases, the time of that collision is also increasing. So the momentum change, which is the impulse, as the what you want to do is when your momentum goes from one side, from some value to zero, you want to maximize that time that it takes to change momentum. So if you're a hockey player or a soccer player, when the ball comes in, you want to cradle it to increase your time of collision. Because if you just keep your stick or your foot flat, it's just going to bounce off and all that energy is going to go right back into the ball. Same with if you're trying to catch something, right? If you were trying to catch a bullet, or a baseball probably is a better example, catch a baseball with your bare hand, if someone was throwing it super fast, you're going to want to bring it back and kind of like collapse with the collision, which is why old cars, like big 50 style steel frame cars, were so massive and they were so dangerous because they were built so strong that they would just, all of the momentum would go into another car, where our modern cars are built with crumple zones, where the hood is designed to break in such a fashion that it's going to increase the time of collisions and then limit the force on the passenger. So before we start talking about collisions, we should talk about the types of collisions. So there are three types. There's inelastic, perfectly inelastic, and elastic. Okay, so in an inelastic collision, we call that a hit and, the momentum is conserved, but not the kinetic energy. So there's some sort of change in shape or deformation. So like a super ball, or when we looked at that super high slow-mo camera of the golf ball hitting the club, there's a deformation of energy, of shape, and that's where the energy is going to go. We don't know, well, you don't know how to calculate how much energy is lost due to deformation of shape yet, maybe in like second year engineering, but all you need to know is that the energy is going to be lost at some point. So we're going to deal with mostly these two collisions. The perfectly inelastic, that's like a hit and stick collision. So two objects stick together after they're collided. So the momentum of one is plus the momentum of two is equal to its momentum together. And this is, in these types of collisions, the velocity both before and after the collision, of the two objects after the collision is the exact same. Okay. So this is like, if I shoot a bullet into a block of ballistics gel that's sitting on a frictionless table, if I shoot a bullet into it, all of that momentum of the bullet is going to go into the ballistics gel, and the ballistic gel will be sliding across the table at a certain velocity. But because the bullet is stuck within the ballistics gel, it didn't go through. Both the bullet and the gel are traveling at the exact same velocity. We're going to do an example later in this lesson where a goalie catches a puck in the collision, and they're going to move backwards at a certain velocity, right? Because both the puck and the goalie are essentially one object at that point. Then elastic collisions are like glancing collisions. So when two objects come together and then bounce off, or if they're coming at an angle, they're going to come and bounce off at two different degrees. In this case, the momentum and the kinetic energy are conserved. So you'll see in calculus, I think you guys have gotten to this point. But so in calculus, this little dash that's on here, and there's one that should be right here, means prime. So basically, it's just another type of language we're going to use to denote after the collision has happened. Okay. So in this case, this equation is formed because we're saying, okay, the momentum in one, the momentum of m1 v1 plus m2 v2 is conserved. And then after the collision, that momentum has to go somewhere. So we're going to say m1 v1 prime. So this is the speed of the first object after the collision. And this is the speed of the second object after the collision. Okay, so let's just do an example. So I'm going to try something new that I think we can do on our office hours. So if I just go on my iPad here and go here, so you should be able to see what I'm writing. So in this case, if we go back, there is a truck stopped at a stoplight. So at a stop sign, there's a truck stopped. Okay, and so when that truck is stopped, there's a car stopped. A car is stopped that has a mass of 1,500 kilograms and then gets slammed into by a truck that is 3,500 kilograms. And we know that the truck initial velocity we don't know of the truck. And the initial velocity of the car we know is 0. We know that the final velocity of the truck after the collision is 6 meters per second. We're assuming it's forward. And so what the question is asking for, it's asking for the final velocity of the car after the collision. Okay, and so all we're going to do is we're going to say M1. Well, first we know that the total momentum before the crash is equal to the total momentum after. Okay, so in this case, the total momentum of the collision is both the truck and the car at the same time. So the momentum of the car plus the momentum of the truck is equal to the momentum of the car prime, which means after the collisions, plus the momentum of the car truck prime. So now we can just go through and say M1 V car plus M2 V truck is equal to M1 V car prime, which is after the collision, plus M2 VT prime after the collision. Okay? Now we can go through and we say, okay, because the initial velocity is 0, there's no momentum. So all of the momentum in the system is coming from the truck initially. So 3,500. Do we know how fast the after? Oh, so we're asked to find the velocity of the truck before the collision by using the momentum after the collision. So in this case, the car is 1,500. And the velocity of the car after is, let's say it's 2 meters per second. Plus the truck's mass times 6 meters per second. So the total velocity is just going to be 3,000 kilogram meters per second, which is the unit of momentum, plus what's 3,500 times 6? Um, 3,500 times 6. So 21,000 kilogram meters per second. And so that means the total momentum is 24,000 kilogram meters per second divided by 3,500. So we're able to find the final speed. So therefore the truck had to be traveling at 6.85 meters per second before the collision. If I scroll down, you can see that. Okay. So this is all using conservation of momentum to calculate things we have before plus things we have after. So let's do this one question together. So a hockey puck, which is 1.5 kilograms, is shot at 80 meters per second. What is the velocity of the puck and the goalie before the collision? So if I go back to my board here, so we have this puck at 1.5 kilograms going towards the goalie. That is just going to be a box with a hole in it right now. Before the collision. And then after the collision, we're going to have one mass with the puck in it, all going at the same velocity prime, which we don't know. And the mass is just going to be equal to M1 plus M2. The goalie is, I didn't write it down, but let's just say that the goalie is 65 kilograms. So we do the same thing. We know that momentum before the collision is equal to the momentum after the collision. So that means M1 of the puck plus M2 of the goalie is equal to M1 VP prime plus M2 VG prime. And so this one, because we know that it's a hit and stick collision, that the mass M1 plus M2, the velocity is going to be the same for both the goalie and the puck. So in this case, 65 plus 1.5, so 66.5 V prime is equal to the goalie's at rest, just 1.5 times 80. So 1.5 times 80 divided by 66.5. Wow. So the goalie is moving at 1.8 meters per second backwards. So that is very, very fast backwards. It's a very fast shot puck. Anyways, so for this week, I want you to do homework. I'll post this on the Classroom in Nicer Writing. Page 231, questions 1 and 2, 232, 2 and 4, and 236, 1 and 2. The page 238 gives you a quick reading synopsis. I'll post those all on the Classroom. There's also a gizmo to be done this week. 4 marks counts as your lab mark. Okay? So we'll be in contact next week when we do this in 2 dimensions. And happy Star Wars Day. Live long and prosper.